Hello! So these are our lecture notes for the remainder of simple harmonic motion. And we're actually going to start back with the review of Hooke's law. So quick remember of Hooke's law, we have that the force in a spring is equal to negative kx. So for a positive displacement, we have a negative force. All right, for example 11.1, we have a family of four that gets into a car. They have a mass of 200 kilograms, and the car has a mass of 1,200 kilograms. When the family gets into the car's springs compress a distance of 3 centimeters. So first we're looking for the spring constant of these springs. So to begin with, let's just make sure we understand that we have force of gravity acting downward, and we have a spring force acting upward. And actually, let's use y instead of x. So what you have here, let's make sure this looks like a y, is a situation where we know that an additional 200 kilograms causes a compression of 3 centimeters. So why is that important? Well, if we look at the sum of forces, we see that k times y minus mg must be equal to 0, because the car is simply sitting there in equilibrium, so that k is equal to mg over y. So our displacement that we know in this case is 3 centimeters, and the force that causes that displacement is the weight of the family alone, not the car. So in this case, we have to use that the mass is only 200 kilograms, and then times our 10 over our displacement of 0.03, and that's meters this time, and we get something that's equal to 6.7 times 10 to the 4th power, and that's newtons per meter. So again, we're getting something slightly different than this because we are using 10 for g instead of 9.8. So now, if instead we used a mass of 300 kilograms, we need to preserve the fact that k is the same, so we're going to carry that over into our situation where we have a sum of forces, and instead of ky equals mg rearranging to find k, we're going to solve for y. So in that case, y would be equal to mg over k. So here, we're just going to simply use the mass of 300 kilograms times our g of 10 over the spring constant we calculated, which was about 6.7 times 10 to the 4th. Of course, I rounded because it was a repeating decimal. And here, our displacement would be the exact same, which is 0.045 meters, or 4.5 centimeters. For our next topic, we will talk about the actual definition for simple harmonic motion, or SHM, as it is probably going to be not so lovingly called. So the quick definition for simple harmonic motion is when an object undergoes oscillations and the restoring force is directly proportional to the displacement. So keep in mind that directly proportional has to do with essentially something that is a direct relationship, or maybe something you would think of as a linear relationship. So in this case, we have a little conceptual example problem to kind of think through this. So for A, we have f is equal to negative 0.5 times x squared. So in this case, if we just kind of sketch out what this would look like, we have a force that is parabolic. In fact, it's negative. So we would have something that looks like this. So our force is not directly proportional. Therefore, this is not going to undergo simple harmonic motion because the force is not directly proportional. For part B, we have now f is equal to negative 2.3y. So what would this look like? Well, this is going to be negative 2.3y, so it's going to go through the origin with a slope of negative 2.3, and this now is directly proportional. So this is a simple harmonic oscillator. If we then go and look at C, the same thing is true. If we graph this, we would have something that is positive 8.6 slope going through the origin, and again, this force is directly proportional to some displacement. Now if we look at D, we have f is equal to negative 4 times theta. So this is a little bit weird, but if you think about theta as just being an angular displacement, then again we just have something that is proportional directly to this angle. So this would in fact be a simple harmonic oscillator because it is directly proportional to something. So in this whole thing, we have a quick summary where essentially, if we have something that is parabolic, that is not directly proportional, therefore it is not going to undergo simple harmonic motion. We would call that some kind of complex harmonic motion because this force is now not directly proportional, but a little bit more complicated. Moving right along, we're going to talk about a very important topic, which is energy in simple harmonic motion. So, as you recall, the force acting on our mass is going to be equal to negative kx, according to Hooke's law. So this force is actually changing as this mass moves. So it's actually very difficult to calculate its acceleration because its force is different at every single location. So instead, it's usually very easy, by comparison, to deal with energy and conservation of energy when analyzing a system that's oscillating. So it's easy because we can take a couple of very critical points and just analyze the energy at those locations and kind of fill in the gaps in the middle. So we know that at maximum displacement, our velocity is 0. So all of the energy of our system is wrapped up in the elastic potential energy associated with our spring. So you may recall that elastic potential energy is equal to 1/2 kx squared, where x is our displacement. So at a maximum amplitude, so our displacement is at its amplitude, this energy is equal to 1/2 k times a squared. So here is that energy at our maximum amplitude. And we don't have any kinetic energy because, again, at this point, our mass is going to be changing directions. It was going left, now it's going right, or vice versa. It was going right and now it's going left. So all of our energy is wrapped up in the potential energy of our system. So you can see these kind of bar graphs off to the side that illustrate this. In the middle, however, at our equilibrium position, so equilibrium position means that our force has now gone to 0, our spring is also not stretched at this location. The displacement is 0. So at this location, all of our energy is wrapped up in the kinetic form. So we have kind of this oscillation actually between the two different forms of energy, potential elastic and kinetic. So that means that anywhere in between these 2 points, a maximum amplitude and the equilibrium position, we have a mixture. So we have a combination of kinetic and elastic potential. So how do we add these up? Well, we know that the maximum energy must be related to the amplitude of the oscillation. So that's why, if you need anything from this slide, it is going to be the fact that the maximum or the total mechanical energy for a harmonic oscillator has to be equal to 1/2 ka squared, where a is the amplitude and k is the spring constant. Hopefully, you remember how to do conservation of energy, but just to refresh you, let's find some examples. So, here's our first example. It's a conceptual one where we're talking about a spring that is being stretched from its equilibrium position to a location that is equal to 2a, so 2 times an amplitude. So what happens to the energy of this system compared to when it was stretched to just x equals a? So our original was right here, and our new version is out here. So what happens to the energy of this system if I stretch it twice as far? Well, remember that our total mechanical energy is equal to that of the elastic potential energy at maximum amplitude, or maximum displacement, which is equal to the amplitude, I should say. So originally, our elastic potential energy was 1/2 k times a squared. Now, our amplitude is our displacement is actually 2 times this amplitude. So our new elastic potential energy would be 1/2 k times 2a. Don't forget to square it. So if we simplify this, we actually see that this elastic potential energy is 1/2 k times 4a squared. So if you compare these two, what's the difference? Well, there's now this factor of 4. So what happens to the energy of the system? Well, it gets multiplied by a factor of 4. So 2 times the amplitude means that I actually have 4 times the total energy. So for B, we want to go on and talk about the maximum velocity. So now we just need to equate our maximum potential energy to our maximum kinetic energy. So if you think about this from conservation of energy, we're simply saying that UE, initial, has to be equal to K, not 1, but 2 at the center point. So let's write this out together. So we have 1/2 K A squared, so this is our original displacement, equals 1/2 mv squared. So some simplification needs to occur. So let's get rid of the 1/2s. And what we end up seeing is that the original velocity is equal to the square root of K over m times, we'll just leave it as A squared. So what happens now when we want to use an energy that is 4 times that? Well, let's go ahead and plug it in and see. So 1/2 K times 2A squared is equal to 1/2 m times, we'll just call this V2 squared. We'll call this V1 while we're at it. So now our 1/2s cancel out again. And if we solve for V2, we see that V2 is the square root of now 4 times K over m A squared. So I can simplify this by pulling the 4 out of the radical. So square root of 4 is 2. So it's 2 times K over m A squared. So what happens to my speed if I pull the amplitude twice as far? Well, it now looks like my speed is multiplied by 2. So there you go. If I double the amplitude, I've doubled the maximum velocity. Now, C is where your first proof of doing this comes in. The maximum acceleration of the mass is going to come from Hooke's law. And what I need you to do is I need you to actually tell me what happens to the acceleration of this mass, or by what factor the acceleration changes, and I need you to submit that for part of this assignment. All right, so for our next example, we have a lot of things going on where we're essentially just finding a lot of different bits of information about the same problem. So we have a spring that stretches 0.15 meters when a 0.3 kilogram mass is suspended from it. Now we don't have the image here, but I can tell you it looks something like this. Here's mg acting downward, here's kx acting upward. And we know that from the sum of forces vertically, kx minus mg must equal 0. So for question A, we want to find the spring constant k. So k, according to this equilibrium statement, must be equal to mg over x or y, either way. And so if we substitute these values, we're going to have 0.3 times 10 over 0.15 for a stiffness constant or spring constant of about 19.6, or if we're doing the math, 20 newtons per meter. For question B, you really don't have any work to do. So it says that this mass is pulled so the spring is stretched 0.1 meters from the equilibrium point and released from rest. So keep in mind that this is horizontal on a frictionless table. So if this is my setup, here is my spring, here is my mass, here is my table, and I stretch it 0.1 meters from the equilibrium position, then that means that the amplitude of this is simply that amount of stretch. So our amplitude is equal to the 0.1 meters that we have here. Now moving right along, we want to find the magnitude of the maximum velocity. So in order to do that, we're going to go right to conservation of energy. So setting this up, I'm not even going to write the whole conservation of energy because I can just go to the elastic potential maximum has to be equal to the kinetic energy maximum for my system. So rewriting this, I have 1/2 kx max. Actually, we can skip ahead and say that's a squared is equal to 1/2 m times v max squared. So let's do the same simplifications. 1/2 goes away, and I'm going to solve for v max. So v max is going to be equal to the square root of k over m times the amplitude squared, or if you actually want to write it out, it would just be the amplitude times the square root of k over m. So let's substitute some values. Vmax then is going to be the amplitude, which we said was 0.1, times the square root of the 20 that we found in part A, over the mass, which was given to be 0.3 kilograms. So plug this into your calculators, and you'll get the answer that we have right above, which was about 0.808, if you round it, meters per second. So, what changes now when you talk about D? Well, for D, it's not as easy as U Emax is equal to Kmax. Now we actually have to say that 1/2 Ka squared, which is our maximum, our total energy, is equal to 1/2 K times our displacement squared plus 1/2 mv squared, which is our kinetic energy at some other location. Luckily, we can get rid of all of the 1/2s, and now we're actually going to be solving for the velocity in this case. So let's rearrange it. So v squared would be equal to Ka squared minus Kx squared over the mass m. So solving for this, velocity would be equal to the square root of. So I'm going to go ahead and factor out the k just to write this a little more neatly. 20 over the mass, which was 0.3, times the difference in my amplitude and my position squared. So my amplitude is 0.1 squared minus 0.05, which is my displacement, squared. And you plug all this in, be careful with the calculator, and you should get about 0.7 meters per second. All right. Now, E asks us for the magnitude of the maximum acceleration. Now, throughout this, in part A, we used G as 10. In part C and D, we used our same K, which was not 19.6, and we just said that the answer was about 0.08, or 0.808, and for D, 0.7. So these answers are not necessarily consistent with the K that we wrote. However, they're close. So the second part of this assignment will actually be to tell me the correct answer for E using your correct numbers. So I'm going to do a little bit of the work, but you have to do the final steps. So the magnitude of the maximum acceleration, remember, comes from, comes from our F equals negative kx, which you should also remember is equal to ma by Newton's second law. So using that, I believe every person should be able to tell me the correct answer for E using our K value of 20. So now you have two different things to turn in for the haiku assignment for this problem. So I know we skipped over a slide, however, we can work on that at a later date. For this last bit, we're going to start talking about period and frequency of our oscillating system and what those depend on. So when we talk about a mass in a spring oscillating, we actually only care about two things. We care about the mass attached to that spring, and then we care about the stiffness of that spring. And the important thing to pull out of this is what happens when I change one or both of these variables. So for instance, if I double the mass, what happens to the period of this spring? Well, 2 times the mass, in this case, would be like plugging in 2m to this. So compared to just having m, what happens? Well, we actually have root 2 times the period. So 2 times the mass doesn't necessarily double the period, but it does increase the period. So another way we might ask this is, well, what happens if I quadruple something? Well, what if I have quadruple the spring constant? Let's actually get rid of these x's. What does that do? Well, it's like plugging in a 4 here. So compared to the original K, what ends up happening? Well, if I quadruple the stiffness of the spring, I could put a 4 in here, and that would be pulled out as a half. So it's actually 1/2 the period. So a stiffer spring leads to a shorter period, and then you need to be able to translate that to frequency. A shorter period is a higher or faster frequency. So when we were talking about a mass spring system, we also probably mentioned a pendulum as another very common oscillating system. So here's a diagram of a pendulum with a bit extra. So we have our free body or force diagram acting on our pendulum, where we have mg acting downward and the force of tension acting along our string towards some point up here. The restoring force in this case is this component of gravity, because this is the force that is acting to move the pendulum back to its equilibrium position, which would be some here, or right here, where the pendulum is straight downward from its string. So this right here is our restoring force. And it may not look directly proportional because of our sine theta. So if you remember, a sine function is actually a little curved. It's not direct. However, we can get around that by noting that a sine is actually very similar to just theta for a very small angle. So essentially what we're doing is we're saying that simple pendulums are going to be simple harmonic as long as the angle that the pendulum makes is small. So you can see in this table what small is. So for a 1 degree different, or 1 degree displacement, we have a 500 or 5,000ths of a percent difference. So that's tiny. 5 degrees, 1/10 of a percent. 10 degrees, 1/2 of a percent. That's really not much. So we can get away with this pretty easily because a small angle can be pretty much as high as 20, maybe even sometimes 25 degrees. So we can do the same thing that we did with a mass spring system for a simple pendulum as an oscillating or simple harmonic oscillator. The difference between our mass spring system and our simple pendulum is what actually affects the period of this pendulum. So there are only 2 things that affect this pendulum, or the period of a pendulum, and that is, of course, the length of our pendulum, and the second is actually the acceleration due to gravity. And so this is a little bit unintuitive because you might think that the mass or even the initial amplitude affects our pendulum, but we're going to prove in laboratory next week that neither of these actually do affect the period of a pendulum. So similar to what we said before, you need to know how changes in one of these variables affect the period of a pendulum. So let's give a different example. So this time, let's say that I want to say, I'm going to take my length and I'm going to multiply it by a factor of 3. What does that do to my period? Well, if I put a 3L instead of just an L, what I end up seeing is that the difference is just a root 3L. So 3 times the length actually only increases the period by a factor of square root of 3, which is less than doubling. We can do the same thing for G. So let's say that I go to the moon. What happens on the moon? Well, here G is equal to 1/6 R's. So it's 1/6, let's see, G moon is equal to 1/6 RG. So what's going to happen to the period here? Well, that is the final bit of your assignment that lets me know that you went through all of this video. So I want you to tell me by what factor the period should change if our acceleration has now become 1/6 of the normal G. To wrap this video up, we have a single example problem for a pendulum. So our simple pendulum has a length of 37.1 centimeters. So our length we're going to write as 37.1 centimeters or 0.371 meters. The frequency of this pendulum, meaning how quickly it goes back and forth, or essentially how often it ticks, if you think of it as a clock, is 0.8190 hertz at a particular location on Earth. From this, we want to calculate the acceleration due to gravity. So, the equation we're going to use is that of frequency. So frequency in this case is equal to 1 over 2 pi times the square root of g over L. So here we're going to be solving for g. So let's go through that together. So first I'm going to multiply both sides by 2 pi. So I have 2 pi times the frequency is equal to the square root of g over L. From here I'm going to square both sides. So I have 2 pi times the frequency squared is equal to g over L. And finally multiply both sides by g. So what I have is g is equal to L times 2 pi times the frequency all squared. Or I could write this as L times 4 times pi squared times the frequency squared. So substituting some values, our length of 0.371 times 4 times pi squared times our frequency of 0.8190 hertz should give us this value right here for g. So, you may be wondering, do I need to memorize this equation? Well, not really. The period equations for both the pendulum and the mass spring system are given on the AP equation sheet. However, you should probably attempt to memorize at least if it's g over L or L over g, so that you can decide how certain variable changes affect the period of those systems. So, in summary, for simple harmonic motion, you should know the following things. You should know the definitions that we've used throughout this part of the unit. You should know how to determine period and frequency for both a mass spring system and a simple pendulum. Now you should also be able to calculate, or at least describe, where or when in a cycle these different systems have a maximum or minimum force, maximum minimum velocity, maximum minimum acceleration. You should also be able to do the same maximum and minima discussion for the kinetic and potential energies for objects such as a mass spring system or the simple pendulum. You should also be able to describe specifically when something is undergoing simple harmonic motion, whether that's due to a directly proportional force or a large or small angle of displacement. Hopefully you enjoyed this video. Please re-watch it if you have any questions for this part of the unit.